A diver stands on top of a 4.6 meter long diving board. The diving board is supported by two brackets as shown in the picture above. Let's call them left and right. The diver has a mass of 50 kilograms, it says, and the board has a mass of 25 kilograms. What is the value and direction of the force on each bracket exerts on the diving board? So this is akin to what is often called like a scaffolding problem or one of those. It's a balancing of torques. So let's think of all the forces involved in here. We've obviously got a force of gravity on the diver. I'll call that FGD for force of gravity on diver. We've got a force of gravity on the board, so I'll label that FGB for force of gravity on the board. And we've got some torques here, or some forces by these brackets. Now, what direction are they? Well, let's pick a pivot point. So let's imagine we pick that left one there as the pivot point. Well, here are two forces causing it to torque counterclockwise. So what direction must that be to keep everything there? This must be an upward force. So let's call that force right. It's got to be up. But I could have just as easily picked this as my pivot point. And if that was the case, then these two are still trying to torque it clockwise, so this one must be providing a force back the other way. So whereas this bracket actually pushes up on the board, this bracket over here must actually be pulling down on the board, and let's call that force left for that one. They've got some distances labeled on here. Between the brackets is 1.2 meters. Between the right bracket and the diver is 3.4 meters. And since the board itself has mass, we need to realize that from the edge of the board to its center of mass, it's 4.6 meters long, so 2.3 meters from the edge to the center of mass there is the where that force is acting on that center of mass. And what may become important later then is this distance right here from this bracket to the center of mass. So since that's 1.2 and we got to go out 2.3, from this bracket to the center of mass is 1.1 meters. So let's now go there and set this up. We're going to balance the torques. I'm going to start again with this left one as my pivot point. So what I'm going to say is that the torque here from the right one is going to balance out the torque from the board plus the torque from the diver. So the one trying to torque it counterclockwise is balancing the two trying to torque it clockwise. So let's plug in for each of these. This would be the force of the right bracket times the lever arm of the right bracket times the sine of the angle between those two. This would be the force of the board times the lever arm of the board times the sine of the angle between those two. And this would be added to the force of the diver times the lever arm of the diver times the sine of the angle between those two. Now, all of these forces are acting at 90 degrees, so those sines of 90s are just going to become ones, and we can just forget about them. So let's start to plug in then for this. So what we're going to do here then is say the force of the right one is what we are looking for. The lever arm of the right one, since this is my pivot point, is 1.2 meters. And that's got to be equal to the force of the board. Well, if it has a mass of 25 kilograms, it has a weight of 250 newtons. And it is a distance 2.3 meters from that far edge left bracket there. That's where the center of mass is. The diver, they have a mass of 50, so they have a force of 500 newtons. And they are a full 4.6 meters out from the edge there. So now we have everything written down except the right force. So we can do some algebra and solve for that, and you should get 2,395.8 newtons there. And so that is the value of the right force. So now it says get both of them. How are we going to get the left force? Well, you can go and you can set it up as a torque problem all over again and solve it this time with the right one as a pivot point, for an example. Or you can make that the pivot point or that. But the easiest way now to go about solving this is just to realize this, that the sum of the forces in the y direction have to add up to be 0 because it's not accelerating in the y direction at all. So we already know what these are. Look, we've got 3 down forces that got to balance out with our 1 up force. So another way to write this statement would be that the force on the right is equal to the force on the left plus the force on the board plus the force on the diver, because I moved all of these negative guys over to the other side already. And we know all of these values except the force on the left there, so we can plug in. We've got 2,395.8. That's got to equal the force on the left. The force on the board is 250 newtons, and the force on the diver is 500 newtons. So everything's there except for the one unknown, so do some algebra, and you'll get the force on the left is 1,645.8 newtons. And again, you could have solved this as the pivot point and solved it this way, and then use this method to find that one, and it would all still work out there. So next question here says, if the diver backs away from the edge of the diving board, what will happen to these two forces, and justify your answer. I'm actually going to do it right here. If we look at this equation here, if they back away, they're going to drop their lever arm. So this whole term here is going to go down. That means this whole side's going to go down, which means this side's got to go down. So the force on the right will go down. And if that one goes down, then we need less of this force on the left to help balance out the upward force. So everything is going to drop there. So last one here says, what if the force on the left bracket can only be a maximum of 2,500 newtons before it breaks? So how much mass can the diver have in order to keep it from snapping there? So let's just set it up again real fast. If that is the case, we have our maximum force here. I am going to pick this right bracket as my pivot point right now. So there is my torque on the left, has got to balance out with my torque from the board here again, plus the torque from the diver. So plugging in here, the force on the left times the lever arm on the left, forget the sign of the angle, we already know about that. It's going to be the force on the board times the lever arm on the board, plus the force on the diver times the lever arm of the diver. Now, one important distance that we solved on the other page is that from this fulcrum, if we consider the right one the fulcrum, to the center mass of the board is 1.1 meters there. So now we know this force on the left. We're going to set it to our maximum. 2,500 newtons is our maximum. Our lever arm is labeled on the diagram, 1.2 meters. The force on the board would be 250 newtons. The lever arm of the board would be 1.1 meters. We're looking for the force of the person. Actually, they say the mass of the person, so we got to do mass times gravity. And the lever arm of the person would be right here. It's labeled from the right bracket to the person is 3.4 meters. So we know everything but mass here. So plug it all in. Do some algebra, and you should get 72 kilograms is the maximum mass that the person can have before the bracket would break.